In this section, we're going to study questions that can be answered by Euler's theorem, which is a key result from graph theory. Alright, so here's our graph theory problem. Let's think about a mail carrier who needs to make mail deliveries along a route each day. One thing that he would be interested in is an efficient route, and for him this would mean visiting each of his delivery mail locations without repeating any of his routes. Alright, so he doesn't want to walk the same sidewalk like 7 different times just to get to some different houses. Alright, so if we rephrase this question as a graph theory question, if we call the delivery locations vertices, and if we call his routes the edges, then we're interested in a route that visits every vertex, we don't want to miss any, without going over any of the edges more than once. So how will we solve this problem? We can use Euler paths and Euler circuits to answer this, so we need to know what those are, and then we'll use Euler's theorem to decide if this type of route is possible, and then Fleury's algorithm to find this type of route. Alright, an Euler path is a path that passes through every edge exactly once, every edge in the graph. An Euler circuit is a circuit that passes through every edge exactly once. Alright, so let's go back and review. We need to remember what a path and a circuit are. Right, so a path, we said that this was a series of adjacent vertices. Okay, so something like B, C, A, we'll go back to B and then to D. Alright, so I've just made up some vertices here. And this type of edge, or this type of path, doesn't repeat any edges. Okay, so edges are used only once. Alright, so what's different between that and an Euler path? Well, using the edges exactly once, that's covered in both of these definitions. So the key word here that makes the difference is the word every. Okay, so paths don't have to use every edge of a graph. We can just pick or choose some of those. But an Euler path must pass through every edge of the entire graph. Right, same thing with an Euler circuit versus a circuit. Okay, so we know that a circuit is a path that begins and ends at the same vertex. Okay, so if we use that previous example that I've just created, BCA, BD, and then maybe we'll just end at B. Okay, so something like that. All right, now this would only be an Euler circuit if it passed through every edge in the graph. Okay, so here's an example. If this is our graph, then an Euler path would be A, B, E, D, C, E. Okay, so by the time I'm done tracing this path, this Euler path, notice that I've used every edge in the graph, and I also didn't retrace any of those edges. Okay. Then on the right, here's an Euler circuit, and just a quick glance shows that this begins and ends at B. Okay, so we know it's a circuit at least. Now to be an Euler circuit, it's got to use every edge. Right, so B to A, to E, to D, to C, to B, to E, and then back to B, and since we're not repeating any edges, then we must be going along this loop. Alright, how do we tell if a graph has an Euler path or circuit? Well, we have Euler's theorem, and this is something that was proved by the mathematician Euler. And this is called an existence theorem. It doesn't actually tell us how to find an Euler path or circuit, it just tells us whether or not one exists. And we have a number of these in math. Okay, so for any connected graph, it's got to be connected first of all. If all the vertices are even, the graph has at least one Euler circuit, which is by definition also an Euler path. The Euler circuit can start at any vertex. Okay. If exactly 2 vertices are odd, the graph has no Euler circuits but it does have at least one Euler path. And that path must begin at one of those odd vertices and end at the other one. If there are more than two odd vertices, then there are no Euler paths and no Euler circuits. Alright, so let's break this down. First of all, why does it have to be connected? Well, we're looking for a path or a circuit that uses all of the edges. Okay? So if we had a disconnected graph, like let's say we had like a little triangle piece and a square piece with some vertices, okay, there's no possible way to come up with a path that uses all of those edges because I can't get from one piece of the graph to the other one. All right, so that's automatically disqualified. All disconnected graphs, we can say right away, no Euler paths or circuits for those graphs. All right, now if it's even, we do have at least one Euler circuit, okay, and we can start anywhere to be able to find that circuit. Okay, if two vertices, exactly two, are odd, okay, think about why we couldn't have an Euler circuit if we had exactly two odd vertices. Okay, so let's try to draw one. Okay, so here's a graph that has, in the square we've got 4 even vertices, and then these two are odd. Okay, they just have one edge coming out of them. Alright, so why couldn't we get an Euler circuit in there? Well, if it's a circuit, then we need to sort of begin and end at the same place, alright, and I can't do that with those two vertices, because if I'm going to, like, say I'm going to begin at this first one, alright, this first odd one, now I can leave that vertex along its one edge, but I can't actually return to that vertex. So that would tell me that I've got to end somewhere else. And same thing with this other one. Alright, so it's possible to get a path in there. Okay, we could start at one and end at the other, but no circuit. So it kind of has to do with the leaving and going from the vertex. And let's say we had a vertex with 3 edges. It doesn't just have to be one edge. And if I'm going to try to get an Euler circuit, well, I can come into that vertex on one of those edges, right? And I could leave on another, and then eventually I could come back to that vertex, right? But there would be no way to leave again, to be able to finish my circuit. Okay. All right, so let's focus on the vertices as we're trying to decide whether or not a graph has an Euler path or circuit. Okay, so this graph on the left, let me count the degree of all of the vertices first. Okay, so vertex A is degree 2. Vertex B is degree 4. C is 2, D is 4, E is 2, F is 4, and that's all of them. Okay, so all the vertices are even, so that tells me that this does have at least one Euler circuit, and by definition that's also a path. Okay, the graph on the right, C is degree 2, D is degree 3, E is 2, F is 3, A is 1, and B is 3. So there are definitely more than 2 odd vertices, so this graph has no Euler paths or circuits. No Euler paths or circuits. Alright, so if we determine that a graph does have an Euler path or circuit, how do we find it? Alright, well, we have Fleury's algorithm to be able to do this efficiently. And for small graphs, you may be able to just do this on your own and figure this out without any help, but keep in mind that graph theory was created to answer all kinds of questions, and we may be dealing with graphs that have hundreds of vertices and hundreds of edges, so in that case we would need an algorithm to be able to find a path or a circuit. Okay, so to find one, if a graph has no odd vertices, then you can start at any vertex, but if it has 2 odd vertices, you must start at either odd vertex. Then we want to number the edges as we trace through the graph, making sure not to traverse any edge twice. All right, so numbering is going to help us keep track of which ones we've used already. And at any vertex where you have a choice of edges, choose one that is not a bridge for the part of the graph that has not yet been numbered. Okay, so we'll practice and try this out. Okay, so use Fleury's algorithm to find an Euler path or circuit if one exists for this graph that's shown. So let me check the degrees first to see where I need to start and if this is even possible. So A is degree 2, B is 3, F is 4, D is 2, E is 2, and C is 3. So this is the case where I have two odd vertices, B and C, so I must start at one and end at the other. Alright, so you can take your pick. I will go ahead and start at B. Okay. And then I'm going to number the edges as I go. And if I ever have a choice, I have to choose one that's not a bridge for the part of the graph that's not yet been numbered. So here, none of the graph has been numbered. I do have a choice of edges. I can choose this one, or this one. Okay, so what I want to do is make sure that I don't choose a bridge. Okay, so if I removed AB, okay, we can quickly sketch what that would look like. I'll draw an extra little graph up here that we can refer to. Okay, and if I were to remove AB, okay, then my graph is still connected, the part that's left. Okay, so I could choose that. If I remove BC, graph is still connected, that looks good. And if I remove BF, the graph is still connected. So in this case, it doesn't matter. You can choose any edge to begin. All right, so I'll go to A, and I'm going to number that 1. Then at A, I don't have a choice. I must go on to C, because remember, we can't backtrack and repeat an edge. Okay. C, I have a choice, so I want to see if either of these edges is a bridge for the part of the graph that's not yet been numbered. Okay, so I've already numbered this part of the graph. I'm going to get rid of those two edges. And let's look at the piece that's left and see if either edge is a bridge. Okay, so if I erase BC, okay, that's not a bridge. And if I erase CF, that's also not a bridge. Okay, so either one. I'll go back to B. Alright, and then from B, I only have one other edge to choose, so I go on to F. Again, at F, I have a choice. So let me look at the part of the graph that's not yet numbered. Okay, and let's see, is FC a bridge? Well, if I erase FC, that actually is a bridge because that would leave vertex C disconnected. So I can't choose that one. Hopefully I can choose FD. And if I erase that edge, the graph is still connected. Okay, so I must go on to D. And then from D, must go on to E, then E to F, and F to C. And notice we did end up at the other odd vertex as promised by the theorem. Okay, so there's our Euler path or circuit, and if we wanted to label this correctly, we would list all the vertices in order, separated by commas. This would be the path B, A, C, B, F, D, E, F, C. All right, and we'll try another example. A mail carrier has the neighborhood pictured in this figure on his route. He wants to cover each street exactly once without retracing any street. Find an Euler path to accomplish this. All right, so let's draw a graph first. Okay, and I'll simplify. We've got all of these different streets, and since the streets are the different edges, okay, then the vertices, let's put those where the streets intersect. Okay, and then we'll connect those with the streets. Alright, so here's my graph, and I've labeled the vertices, and I've just chosen capital letters. You can label those in any order using any letters that you would like. Okay, so first of all, is an Euler path even possible? So let's check that first. Okay, so let's check the degrees. A is degree 2, B is degree 2, C is degree 2, D is degree 3. Okay, so I've got one odd so far. Right, E is degree 3, that's odd. F is 2, G is 2, and H is 2. So this is possible. It's going to be an Euler path, not a circuit. And I need to begin or end at D or E. Okay, so let's begin at E for something different. I'll start there. And then I need to look at the pieces of the graph that are not yet numbered to see if any of the edges that I can choose would be a bridge. Alright, so I'll recopy this real quick. And I think you can probably tell one of these edges is a bridge, so I can't choose that. Alright, so if I chose edge DE, okay, let me erase that. That actually is a bridge. Erasing it gives two pieces to the graph, so I can't choose that. EF looks okay, that's not a bridge, and neither is EH. Okay, if I take that out, graph is still connected. Okay, so you have a choice. I'll go from E to F, call that 1. Oops. Okay, and then F, I don't have a choice. I must go on to G, and then G to H, and then H to E, and then E to D. And then I have a choice again. So I look at the part of the graph that's not numbered, just this part on the left. And DA is not a bridge. Okay, and neither is DC. So either one is okay. So let's do DC, and then C to B, and B to A, and A to D. Okay, so that gives me all of the edges, and I haven't used any of them more than once. I've confirmed that by numbering them. So final answer, the Euler path would be E, F, G, H, E, D, C, B, A, D. Okay, now that's just my answer. There are certainly other paths and circuits possible in many of these graphs. So what I would be looking for is just to see, is this an Euler path, meaning it uses every edge exactly once, right? Or an Euler circuit, every edge exactly once, and returns to the same vertex at the end. Okay, and if you've met those requirements, you've found an Euler path or circuit. Alright, so that's the gist. We know what an Euler path and an Euler circuit are, and then we have two major results to be able to determine if these exist, and to find one, we've got Euler's theorem and Fleury's algorithm.